This is the first lecture on a Zener diode, and before I talk about exactly what a Zener diode is, I just want to review what we've covered so far as in regard to current versus voltage for an ideal diode and an actual diode. So here in the black, that's the plot that represents the ideal diode, where when it's forward biased, it acts like a short, so there's 0 volts across it no matter what the current flowing through the ideal diode is. And then when it's reverse bias, ideally there's 0 current through the ideal diode no matter what the reverse bias voltage is. Now in the actual case, like we've gone over, the primary difference is what happens on the forward bias side is that the diode doesn't turn fully on until there's this forward bias voltage that's indicative of the energy required to overcome that electric potential barrier at the junction that we went over. So again, this V gamma, that would be the 0.6 volts or 0.7 volts for a silicon diode. And then in the reverse bias region, in the actual case, instead of 0 current, there's a very small amount of current. But again, in this class, we just assume that the actual and the ideal are the same on the reverse bias side. But what we haven't talked about is that there's something very interesting that occurs when the reverse bias voltage is relatively large. Okay, in this region of the curve here, we're not quite done. And this is where a Zener diode comes in, because a Zener diode is a special kind of diode that often, most typically operates in this region here, okay, where this interesting phenomenon occurs that we're going to talk about. So here I have a PN junction that's reverse bias. As you can see, the higher voltage end of the source is connected to the N side, which is the cathode of the PN junction, and the lower negative terminal of the source is connected to the anode, the P side of the junction. Now here's the circuit symbol for a Zener diode. Okay, it looks very similar to a regular diode symbol, except there's these fins that are on the cathode part of the symbol. So this is the cathode part here, and this is the anode. Okay, so those little fins indicate that it's a Zener diode as opposed to a diode that's not a Zener, okay, which we've talked to up to this point. Well, if you look at what happens with the free charges when you have a reverse bias case, ideally all your free electrons on the inside migrate over to the far end of the N region, and all the positive charges migrate to the far end of that P region, because these positive charges are attracted to the excess electrons that are on the negative terminal of the battery, and these free electrons are attracted to the excess positive charge that's on the positive side of the battery. So you see, ideally there's no charge that passes through the junction here, and that's why we say that when an ideal diode is reverse biased, you don't have any current at all. Now in the actual case, due to mainly thermal effects, you do get a small crossing of free charges here at the junction, and that's that little bit of reverse saturation current that we talked about that in this class we just ignore because it's so small. But you see, this isn't the entire story, because if this reverse bias voltage becomes large enough, okay, and again, think of voltage as being pressure. So if we put enough pressure across this junction, eventually what will happen is that electrons will be ripped from their covalent bands on both sides of the junction. So what you get are electrons that are being ripped like this on both sides of the junction. And now you have electrons flowing through this junction, and if there's electrons flowing, there's also positive charges flowing. So as electrons flow one direction, as we've talked about and as you learned about in your circuit theory classes, right? As electrons go one direction, the positive charges are going the other direction, right? And we've defined in this class, just like in your 201 class, that current is positive charge flow. So you see, once this ripping of electrons occurs, and when this occurs, it tends to happen all at once. In fact, it's referred to as an avalanche current, okay? Because as a free electron is ripped out of its orbit, it bumps into a nearby electron, knocking it out of its orbits, and it's just a continual effect, just like an avalanche coming down the side of a mountain. So the effect is that now there is a current flowing, and the current that's flowing, it's a reverse bias current. So this current is actually going against the arrow of the symbol. Okay, it's flowing cathode to anode. It's very important to make the distinction that, excuse me, that before today's lecture, we only talked about forward bias current, which flows anode to cathode, okay, over in this region of the IP curve. But here we have a current under this special condition, and it only works for a Zener diode, because if we don't have a Zener diode, the junction's not going to be strong enough and the diode will become defective. So you see, Zener diodes are specially fabricated to be able to withstand this avalanche current and remain robust enough where they still will function. Okay, a normal diode, a diode that's not a Zener diode, would become defective once this avalanche current would start to flow. It would essentially burn up, and your junction would be no good and your diode would be defective. Okay, but with the Zener diode under this condition, we do have a current flowing cathode to anode, and that's a reverse bias current. Now, ideally, when this current starts to flow, it starts to flow instantaneously. Okay, so ideally we would show this instantaneous current as just a vertical line straight down, and the reverse bias voltage at which this occurs is the Zener voltage VZ. Okay, now in actuality, that onslaught of current, that avalanche current, it doesn't happen instantaneously, but it happens really quickly, and that's represented by, you know, a very steep line, but it's not perfectly vertical. You know, there's some slope to it. So as far as analysis purposes goes, when we have a Zener diode in a circuit that's reverse bias and conducting, okay, reverse bias current flowing cathode to anode, well, we represent that Zener diode with a voltage source of value VZ, because ideally once the Zener diode starts to conduct, no matter what the current is flowing, that reverse bias current, no matter what it is, will have a constant voltage VZ across it. And that's the definition, that's the current voltage definition of an ideal voltage source that you learned back in 201. That an ideal voltage source has a constant amount of voltage across it, no matter what the current flowing through it is. You see, in the actual case, you know, depending on what the current is, the voltage across the Zener will vary somewhat. You know, it will vary typically, you know, a couple tenths of a volt. So even in the actual case, the Zener diode is very close to the ideal. And in this class, we're only going to worry about the ideal. So that was the physics behind a Zener diode. Now, as far as when we do problems involving Zener diodes, we're going to use a model just like we used a model for regular diodes, okay, non-Zener diodes. I just repeated the ideal diode model here, as you can see. This is the same as we had in our notes earlier in the quarter. So as you may recall, and again, this is just a summary of the IV characteristics of an ideal diode, that when it's forward biased, when this voltage VD, which is just VA minus VK as we said before, okay, this is just VA minus VK. Again, A is the arrow side of the symbol, K is the line side. Okay, so if that diode voltage is greater than or equal to 0, it's forward bias acting like a short. If it's less than 0, that diode voltage, well then it's reverse bias acting like an open. Well, here's the ideal Zener model. So let's see what's the same and what's different. Well, like we talked about before, the symbol's a little bit different. There's these fins that indicate that it's a Zener diode, but that line side is still the cathode side and the arrow side is still the anode side. VD is defined the same way, okay, so that the anode's at a higher voltage than the cathode. That's how it's defined. So when it's forward bias, you're going to get a positive amount. So if it's a positive amount or equal to 0, it's forward bias acting like a short. So you see that's exactly the same as a non-Zener diode. What's different is the reverse bias region, because now you have two different regions with the Zener diode. If the diode voltage is between 0 and the VZ amount, remember the VZ amount, that's the reverse bias voltage that will get the ripping of electrons to occur, just to occur, and at that point the Zener diode is conducting. So if I have a reverse bias voltage that's between 0 and what that absolute minimum necessary amount to get the avalanche current to flow, well then the Zener's reverse bias acting ideally is an open. But once I have enough reverse bias voltage, okay, VZ is just enough, so if I have VZ or if I have more reverse bias voltage than VZ, well that's when the Zener's reverse bias, but it's conducting and it acts like a voltage source, an ideal voltage source of VZ. So you see here, this is reverse bias conducting, you know, current's going to be flowing. Now you may recall that with a non-Zener diode, and this would be true for a Zener diode as well since they're the same in the forward bias region, but in the actual case we represent a non-Zener diode with a voltage source of 0.6 or 0.7 volts when it's conducting in the forward bias region. Okay, and you would do the same for a silicon Zener diode also, although Zener diodes are primarily used in a reverse bias region, okay, because that's where they have their unique characteristic, again, that they'll allow current to flow in the reverse bias direction without being physically harmed. But you may recall in the actual forward bias case with a non-Zener diode, we would represent that diode with a voltage source of value 0.6 volts or 0.7 volts. And that's because once that actual diode turned on, well, it would maintain that constant amount of voltage, 0.6 or 0.7, no matter what the current, no matter what the forward bias current was. Well here, this is a reverse bias current where we have a constant amount of voltage VZ, no matter what that reverse bias current is. Now, with the actual forward bias diode, we would put the plus side of this source with the anode, okay, because current was flowing anode to cathode. So as current flows through the diode, you're dropping voltage. Well here, with the Zener diode, when there's reverse bias current, the current is flowing cathode to anode. Okay, see the current's flowing cathode to anode. So when you put this source that represents the Zener diode into the circuit, you got to put the cathode to the plus side, okay, because again, as current's flowing through the Zener, as this reverse bias current's flowing through the Zener, you drop voltage. Okay, no kind of diode, whether it's a regular diode or a Zener diode, diodes, no matter what type it is, they can't supply power. So you're always going to have current flowing from the higher voltage end to the lower voltage end, whether it's forward bias or whether it's reverse bias. Okay, the last thing here is that on a spec sheet you'll see the value of VZ. Okay, VZ is a specification. It's something that's a given in a problem, or you know, if you're doing something in industry, you would just look on the data sheet what the VZ is for a particular Zener diode. And on the data sheet, VZ is going to be given as a positive number. However, for this model to make sense, you got to put a minus sign in front of that VZ value, right? Because remember, here minus means reverse bias. So in this model here, it wouldn't make sense for these two reverse bias cases if VZ was a positive amount. So if on a data sheet, for example, you're given VZ is 12 volts, well, in this model, you would just plug in minus 12 volts. Okay, just a little little factoid that if you don't realize this, it can cause some confusion. And this will come up in some problems that we're going to be going over in future videos. And like I said, this is just the first video on Zener diodes. The next several videos will be dealing more with Zener diodes.